This is the recording for section 9.2, the ellipse. And here's, again, new words, ellipse, focus. Actually, the ellipse has two focuses. They're called foci. Has a major axis, which is the long one here, the longest, so to say, radius, but let's not call it radius, let's call it major axis. And then the minor axis. So these are the new words that we have here. And then there are the vertices. The vertices are the ones that are furthest out. By the way, the circle itself is a special case of an ellipse. It is an ellipse with the two foci being at the center and the major axis being the same as the minor axis. Hence, all the radii or all the diameters are the same, and that's a circle. We can see that later, how the two relate with the equation. Okay, but the first thing they're going to do here in the book is a derivation of the equation for an ellipse, and it has a special property that if you grab these two foci and you connect them here via a point of an ellipse, then that distance here, d1 plus d2, is always the same no matter where it is. So if you draw it here, or if you draw it, let's say, over here, then this short distance plus this long distance here will be the same no matter where you are. So d1 plus d2 is the same, and that's where they derive, that's what they use in order to derive the equation of an ellipse, which is here. This is an ellipse, by the way, that is centered at the origin. So it has the special shape of x squared plus y squared equals, divided by a squared and b squared equals 1. By the way, if you leave out the a squared and the b squared and you just have x squared plus y squared, then we have a circle. Again, I will show that later. All right, here is the special case of ellipses where they're centered at the origin, but I like the more general case better, so let's scroll down to that one. And again, they have another table here. So apparently they do make the same table twice. I don't necessarily like this because this one here, the general case, should actually do it. So here it is, x squared right there, y squared right there. Each one of them is divided by a squared, respectively, b squared. That is either the major or the minor axis, depends on if the ellipse is horizontal or if the ellipse is vertical. The difference that they have here, notice they swapped the b and the a over here with the a and the b over here. And in this case, this denominator is larger than that one. And in the other case, this denominator over here is larger than this denominator. And that makes the ellipse either horizontal or vertical. The h and the k that you see here, well, that's the center of the ellipse. And then here the foci are calculated as such, and this kind of gets a little complicated, right? There has to be this other parameter calculated first with square root of a squared minus b squared. Almost looks like the Pythagorean. In fact, it goes back to doing these little triangles that you saw earlier. Actually, that's not true. It actually goes back to this one here, this distance here, minor axis, major axis, and then this distance across here. That's actually the right triangle of Pythagorean. Then there are the vertices, major and minor axis, and so on. All right, the rest is, I believe, examples, lots and lots here. There's actually an application, elliptical orbit of Halley's Comet. I'm not going to promise that we look at it, but maybe we will. Let's see. And then I want to do a couple of exercises, and then I'm going to show a few applications. So let's see, I chose number 20. So this one right here. This one here tells us right away that the center is at -5. Remember, the formula says x minus something. So this one here is -5. And then it says y minus something, which means it's at 3. So the center is actually at -5 and 3. Notice the denominators are nice squares, right? And notice actually almost all the other problems have nice squares there. They do that on purpose because this one here tells us right away that the major axis is going to be 5, because it's supposed to read 5 squared in the denominator. And here the minor axis is going to be 4 squared. So, I'm sorry, 4 is the minor axis, and this, of course, says 4 squared. All right, so let's do this one here. Where am I going to do it? Of course, in Desmos. So here it is. Oops. I didn't mean that to happen. How did that happen? Anyway, So here already is an ellipse, and I didn't write this, somebody else did. I just took it over. Maybe I amended it or just put it in my list. So this one here is called the equations of an ellipse. Perhaps could Google that. Anyway, let's see. So what was it again? H is -5. Here we go. Whoa, being pushed way over there. And K is 3. So over there. All right, by that time, come on, there we go. That time, I guess I can push this one over here. And let's see what else we have. The A was a 5, putting us at a 5 squared. I'm going to double check that. Yep, that's true. So 5 right there makes it pretty long, I guess. But then the B itself was 4, so that's going to also make it vertical. There we go. And there we go. All right, and that's actually it. Let's see if I can center us more. I don't know. There we go. Maybe zoom out a little bit so I have the whole thing here. So the center is over here, -5 and 3 as promised, and then the foci are over here. And let's see, then it also calculates that C. The C is needed in order to figure out where the foci are. Actually, this one comes out easily as 25 minus 16 is 9. And then take the square root, and that of course is 3. That's why you see the 3 there. The vertices are over here, here, and here, and I don't think that actually is computed here, but that's all right. All right, another exercise. So here I'm going to use number 30 on the next page. There it is. Now, is that an ellipse? Yes, it is, because it has x squared and y squared in it, and the two are connected with a plus on the same side. By the way, in the next section where we talk about hyperbolas, you will see that it will be x squared minus y squared, or the other way around, y squared minus x squared. And that will give us a hyperbola. Again, you will see in the next section. Okay, before I put that into Desmos, I will actually analyze it with Symbolab first, because I need to put it into the regular equation that kind of looks like this one here. So we can easily identify the major axis and minor axis and the centers and the foci and the vertices. So this one here kind of looks like completing the square a couple of times. So I'm going to go over here to Symbolab, and I hope I plugged it in correctly. This is actually, I googled Symbolab ellipse, and this is what it comes up with. There it says right there, Ellipse Calculator. All right, so let's do this one. I'm going to type simplify in the front, and let's see what Symbolab comes up with. All right, click a little down. It says, here's the ellipse standard equation. So that's what it aims for. And here it's writing it already. And I like this way that this is written, because this one tells us nicely where the center is, -3 and 2. And it tells us nicely what the major and minor axes are, so 3 and 1. And the 1 over there on the other side, by the way, is standard for both ellipses and hyperbolas, not for circles. Again, I'm going to show that pretty soon. So let's see. Here's the show steps. And as I said, it should complete the square twice. So what it does here is it rearranges the original terms in order that it writes the x's together and the y's together. There we go. And now it completes the square, which is take half of 6, which is 3, and squared, which is 9, add that, and over here it actually factors out first of 9. You can see that one here. And then it takes the 2 here, or the -4, divides it by 2, and that gives us -2. Square that gives us a +4. And that's what it does, kind of. Here and here it actually divides by the 1/9. Okay. By the way, there's here the 3 squared, right, that I promised earlier. And let's see, there's the +4 that I promised a moment ago. It still has that 1/9 here, and then it does a little bit with that. I would have kept it in front here and do that at the very end. And then anyway, it divides by that, and we come up with these denominators: divide by 9, divide by 1. And then it's split up into 3 squared, 1 squared. So let's go over to Desmos and graph that one. Okay, and you're at Desmos, and I actually had to retype this equation again here because it doesn't copy from Symbolab to Desmos or to Word between the three, so every time I have to retype it. Oh well, this, by the way, is the ellipse that we looked at earlier. So I'm going to actually turn this one off. For now, I'm going to turn this one on. So here's our ellipse. That's what we're aiming for. And these are not the foci. These are still the foci from the other one. So actually, let me turn the other one back on. There it is. And let's see, what did it come up with? I'm going to look again here. So it came up with -3 and 2, 3 and 1. Oh, I remember that. So -3. And was it 2? There we go. Yeah, it's getting there. And I'm going to have to make this smaller here. And then 3 and 1, right? So 3, oh, look at that. There we go. And 1. And there it is. And why is it not exact? That's interesting. What happened? What happened? All right, I actually had to pause a few minutes here to figure out why are they not exactly the same. I figure it out. It's the 1 right here. That's not a 1. That's supposed to be a 0. Here in Symbol Lab, I did it correctly. I plugged in the 0 right there. In the book, it's correctly. There's a 0. So let me fix that one here. So the original ellipse actually has a 0 there, and there it is. And so now the two are identical before and after the algebra. Okay, and then after this one, I actually owe you a circle. So I'm going to highlight this one here. So I make one up. I guess I call it problem 95 or so, which is not in the book. Unfortunately, they didn't put a circle in here. We can put the center of the circle anywhere we want. So let's say I'm going to like leave it around here somewhere, right? So maybe K is 4. There we go. And H is, maybe -2. There we go. Okay, good. But what's important is that the A and the B need to be the same. So I'm going to choose this one here. Let's say A equals 2. And this one I choose B equals 2. And we can see that is exactly a circle, of course. And the two foci are actually one and the same. And that's the center of the circle. And this is a perfect circle. Okay, so what I did here is A and B are actually 2. And then I have my center at -2 and 4. So if over here I'm going to rewrite this one here differently, I would come up with, oops, I wanted to erase that actually. Try that again. Please let me erase it. There we go. Maybe. There we go. So x minus -2, parentheses, squared, plus y minus 4. I believe that is correct, my center. And then this is going to be different because the denominators are the same. I can just call them 1, but I would have to multiply with my radius squared. And what was it again? What did I choose? 2 squared, right? Yeah, 2 is my radius, and I need to square that because that's how the equation for a circle would look like. And notice they're identical. This one here versus this one here. And they're back, right? Okay, in the next recording, I will do one more ellipse, a vertical ellipse, and then I'm going to show some applications.